Assalamualaikum warahmatullahi wabarakatuh. Good afternoon, good evening, and good morning, everyone, wherever you are. Let's continue our knowledge sharing on behalf of talk about cap rock sealing evaluation, specifically some uncertainties that may be associated from the properties. Welcome again to my lab reservoir. Today, knowledge sharing, I would like to talk about something related to shale. Actually, this opening slide, there are a number of the book bothering shale. Why do we care about this? In the following story, we are going to deep dive into the uncertainty involved in evaluating the effectiveness of cap rock shale in the Gulf of Mexico, North Sea, and some other areas. The cap rock seals are geological formation that act as a barrier, preventing the upward migration of fluids such as oil and gas from the reservoir. The evaluation process of these shales involve inherent uncertainty, which can impact the accuracy of prediction and assessment related to the hydrocarbon exploration and production. There are two types of top seal in the context of petroleum concepts, capillary or membrane seal, and the second one, hydraulic or fracture seal. Capillary or membrane seals refer to the ability of hydrocarbon fluid to resist displacing water from the pores. The displacement of water from the pores by buoyant hydrocarbon fluids. These seals rely on the capillary force and the resistance they provide to maintain the integrity of the seal and prevent the fluid migration. On the other hand, hydraulic or fracture seal involve the buoyant force needed to surpass the minimum stress and cause of the rock to break or fracture. This type of seal in the geological formation require a buoyant force, both of them, that surpass the minimum stress threshold to fracture or break the rock seal, allowing fluid migration to occur. Understanding hydraulic or fracture seals is very crucial in assessing the integrity of subsurface reservoir, predicting fluid flow pattern in the subsurface. These two types of seals crucial role, especially determining the containment and the migration of hydrocarbon fluid within the subsurface. So, the concept of uncertainty in shale evaluation referred to the variability and lack of precision in assessing the sealing capacity of geological formation in the context of oil and gas. Factors such as interpretation of breakthrough pressure, reservoir condition, experimental data, extrapolation, pressure gradient, stress ratio, and the fluid type prediction contribute to the uncertainty. To address this situation, the seal evaluation process aims to be consistent across different geological basin and tectonic regime, utilizing a probabilistic approach rather than a deterministic one. The capillary pressure seal capacity, which refer to the ability of seal to prevent fluid flow, can vary based on the several factors. These include how the breakthrough pressure is interpreted, the temperature, pressure, and type of hydrocarbon fluid present in the reservoir, and also the correlation and extrapolation of experimental value across the different scale. All of this variation highlight the need for consistent yet adaptable seal evaluation process that consider probabilistic approach. The fracture or hydraulic seal capacity refer to the ability of geological formation to prevent the fluid flow is influenced by three main factors: predicted pressure gradient, effective stress ratio, inferred or predicted hydrocarbon fluid type. These factors determine the sealing capacity of the formation and can vary depending on specific condition characteristic of the reservoir. Understanding and evaluating this factor is crucial. Again, the seal evaluation process for oil and gas exploration and probabilistic approach is used to account for the inherent uncertainty involved. In the context of seal evaluation, the process needs to be consistent, prescriptive across different basin and tectonic regime. This means that while the evaluation approach should maintain uniformity, it should also provide specific guidelines tailored to the unique characteristics of each basin and tectonic regime. Additionally, a probabilistic approach consider uncertainty, assign probability to different outcomes should be used instead of deterministic approach that assume precise and certain result. Now, we are going to see the fluid pressure gradient where the change in pressure per unit distance in a fluid, a given contact pressure gradient, different type of fluids are listed along with the corresponding pressure gradient profile. This pressure gradient indicate how the pressure of each fluid changes as you move vertically upward or downward, with fresh water and seawater having similar pressure gradient, basin brine having a slightly higher pressure gradient, and oil and gas having lower pressure gradient. For the specific gradient fluid pressure, fresh water things is around 0.43 pound per square inch. Seawater is around a bit slightly higher, 0.44. Basin brine also higher, 0.47, and oil has gradient range 0.22 up to 0.37 psi per foot, and gas is slightly lighter density, 0.05 to 0.25. All of these values indicate how the pressure of each fluid changes as you move vertically or horizontally through it, providing insight into the behavior of oil and gas in different environments. In analyzing plots related to the fluid pressure, an important concept is density of the fluids. The slope of the pressure point on the graphs indicate change in the fluid density. Gas column have a lower density compared to the oil column, which is reflected in increased slope on the graph. Additionally, supernormal pressure occurs when the gradient exceeds a certain mud weight, while under pressure, zone with water have densities lower than the of salt water. Pressure gradient for different fluid and the concept of supernormal pressure zone. Pressure gradient represent the change in pressure over the given distance and vary depending on the type of fluid being considered. And the zone of supernormal pressure indicates an area where the pressure is higher than expected. So the pressure exerted by the fluid on the subject submerged or immersed in it is known as buoyancy pressure. It is calculated by multiplying the height of the fluid column by difference in pressure gradient between water and hydrocarbons. PB is equal with Z multiply the gradient, the different pressure gradient water against the hydrocarbon. This equation is used to calculate the buoyancy pressure in example involving oil and gas column of certain heights. For example, when 1,000 foot column of oil, where the buoyancy pressure of this oil column calculated by multiplying column head 1,000 by the pressure difference 0.47 minus 0.3. So the value buoyant pressure, I think, is around 170 psi. In the meantime, 1,000 foot of gas column in the same approach equation will end up with the value 290 pounds per square inch. The water doesn't easily get displaced from the narrow passage called pore throat by fluids like oil and gas, which do not mix well with water. The resistance to displacement occurs because water has stronger affinity for the pore throat compared to non-wetting fluids like oil and gas. So the following written equation that relates the displacement or entry pressure PD of water in solid material to the interfacial tension gamma, contact angle theta, and pore throat radius r. The equation PD equal with 2 gamma multiply cos theta divided with r describe the resistance encountered by water when it displaces or enter the solid material. This equation helps us understand the factors influencing the movement of water in porous media and is relevant in various fields. Measuring displacement capillary entry pressure to a laboratory technique used to determine the pressure required for a fluid to displace another fluid within the porous rock samples. This is typically done by injecting mercury into air-dried seal rock specimen or other type of core sample. The measured displacement pressure values are then converted from the air mercury system to the relevant hydrocarbon water system for further analysis and interpretation. In the laboratory, the displacement pressure, specifically capillary entry pressure, measured by injecting mercury into the shale rock specimen, had been dried of air. This measurement is typically performed using conventional core plot, but can also be done using drill cutting or disaggregated pieces of sidewall core. It is important to convert the measurement from the air mercury system to the hydrocarbon water system for the accurate interpretation and application purposes. This conversion is necessarily to align the measurement condition with the actual condition of the interest, such as oil and gas reservoir. By making this conversion, the measurement can provide, of course, a more accurate and relevant information for understanding the behavior of rock specimen or drill cutting is desired system. The breakthrough experiment, the case involved testing 10 sample of sandstone, shale, and chalk using water and mercury air system. The experiment aimed to determine the minimum saturation level of the non-wetting phase as required to establish a continuous filament across the samples, known as breakthrough. The results show the breakthrough saturation range from 4.5% to 70%, with an average saturation is around 10%. The non-wetting phase saturation refer to the amount of fluid that doesn't easily wet or spread across the porous material such as sandstone, shale, or chalk. In this experiment, it's found that achieve a continuous flow and this non-wetting fluid through the entire ensemble breakthrough, the saturation level needed range from 4.5 to 70% with an average saturation 10%. All of this provide insight to behavior of fluid in porous material, can be useful typical specific gas reservoir engineering for various application fluid flow studies. The given graphic represent related data to the air mercury capillary pressure in a specific case. It shows the capillary pressure values at different wetting saturation corresponding to the pressure in PSI. The data also include measurement from the sidewall core and Pluto well and mention the presence of subsurface crack and detect defect being filled with the mercury. So back to basic definition. When the air mercury capillary pressure refers to the pressure difference between air and mercury in the capillary tube. It is measure the capillary force acting on the interface between air and mercury, which determines the wetting phase saturation. In the given context, the values provided represent the capillary pressure at specific depth in subsurface formation. From the graph, we can see the information about the fluid constant, including oil-water contact, head above contact, densities of different fluid at various temperatures, and also mention breakthrough pressure for gas brine, oil brine system. And specific things highlighted the gas seal, three different sample, 12,000 something, 13,000, 170 foot, and the third one, 13,916, where this shell indicate the depth at which gas is effectively contained by surrounding brine with the breakthrough pressure for gas brines is around 207.20, for all brines 131.81, and the third samples is 290.0.707 psi. Another analysis from these three different samples provide heads of hydrocarbon seal will hold, refer to the maximum vertical distance that a seal can maintain the containment of hydrocarbon without any leakage. It is critical parameter in the context of fluid dynamic and wellbore integrity, as it determines the effectiveness of sealing mechanism in preventing upward migration of hydrocarbon. The specific value for these parameters, as we can see from the slide, sample 12,000 somethings, the gas sales is around 742 feet of gas. The second sample is around 472 feet gas seal. The third sample is much higher, 1,039 foot of gas. Normally, a complete analysis also included the pore through entry radius, microns, refer to the size of the opening or passage in porous material through which fluid can flow. It represents the radius of the smallest opening or throat that allows fluid entry into the pores. These parameters is important in characterizing the permeability and the fluid flow properties of porous media, such as rock. And the specific value for this measurement sample analysis, first sample, the PTR is range 0.035, while the second samples is 0.055, and the last one is at the lower PTR's value around 0.025 micron. A continuous discussion on the conversion of air mercury hydragirum to hydrocarbon to water system. It introduced the equation PC hydrocarbons against water is equal with gamma hydrocarbon water system multiply cos theta hydrocarbon water system multiply PC air mercury divided with gamma air mercury multiplied with cos theta. All of this simple equation for calculating the breakthrough pressure. It's also mentioned the range of gamma oil water and gamma gas water values depend on factors like hydrocarbon type, temperature, and pressure. Provide example of calculating the PC oil water or PC gas water using specific values. The calculation of pressure capacity, PC, capillary pressure capacity for oil and gas case based on the breakthrough pressure values and the gradient range. The formula H is equal with PC sales minus PC reservoir divided with gradient water minus gradient oil or gas is used to calculate the hydrocarbon seal capacity. The calculated PC value for different scenario are provided for both. Some set of detail in the oil case, the interpretation of hydrocarbon seal capacity, the values represent the pressure at which oil would break through the seal given different oil gradient. For example, when the oil gradient is between 0.28 up to 0.37, the breakthrough pressure is range 247 up to 3,290 foot. This calculation, of course, help assess the effectiveness of the seal in preventing oil migration, while the calculation related to the gas case in the interpretation of hydrocarbon seal capacity. The values represent the pressure at which gas breakthrough occurs in feet calculated using the gas gradient range, the difference in pressure between the hydrocarbon and water gradient. For example, when the gas gradient is 0.1 up to 0.25 psi per foot, corresponding the gas breakthrough pressure calculated to be very 532, 895, 786, and also 1,332 foot respectively. One of the critical cell capacities refer to the thinnest layer that has the least restrictive pore radii, which means it's low for the least amount of fluid flow. As we can look at for more detail, questioning how accurately the measured value represent this critical cell capacity, specifically in relation to the measured MIP, mercury intrusion porosimetry value obtained from the shale core sample. The way asking about accuracy of the measured value in representing the critical cell, the following illustration is trying to figure it out to know how closely the measured values align with the properties of the thinnest continuous layer as the least restrictive pore radii, which is known as the critical cell. The question is evaluating the reliability of the measurement in capturing the characteristic of the critical cell. So, the way utilizing and get knowledge from the capillary pressure analysis, the recommendation suggests gathering enough data on capillary pressure to determine the cumulative frequency based on the displacement pressure of air and mercury. Additionally, it is advised to determine suitable interfacial tension values to convert the air hydrargyrum values to the hydrocarbon water system using specific temperatures and pressure condition. Furthermore, guidelines should be established to determine appropriate hydrocarbon fluid gradient for exploration prospect in basin-wide where the fluid data is sometimes limited or even unavailable. To ensemble sufficient capillary pressure data means that to collect enough information about the pressure difference between air and mercury to determine the cumulative frequency. These frequencies represent the number of occurrence of different displacement pressure measured in PSI. The goal is to establish relationship between displacement pressure and the cumulative frequency to better understand the capillary behavior in each system. To convert the capillary pressure data from air mercury to hydrocarbon water system, it is necessary to determine suitable interfacial tension values. This can be done either arbitrarily or through research, considering the specific temperature and pressure condition of the prospect. These interfacial tension values play a crucial role in accurately characterizing the behavior fluids in the hydrocarbon water system. To establish the guideline, determining appropriate hydrocarbon fluid gradient for exploration prospect, especially in the case where fluid data is limited or unavailable across all basins, systematic approach need to be developed. This approach should consider prospect-specific temperature, pressure values, as well as interfacial tension, with the purpose convert air mercury displacement pressure data to the hydrocarbon water system. Overall, this guideline will aid in making informed decision during exploration activities in various geological basins. The following figure shows a graph that represents the relationship between pressure and depth in a well. The graph also includes line indicating different mud weight equivalent freshwater gradient. The point E, B, C, D, and F on the graph represent recorded pressure value at various depth below the sea level. And recognition of sharp shift water lines on pressure depth plot indicate seal capable of holding significant geopressure. The seal above was entered at 3000 psi on freshwater gradient with 8.3 pound per gallon mud weight. When drilling out of the seal at D, the mud weight would have to be increased up to 16.8 pound per gallon to certain the pressure. Where the pressure depth ratio increased from 0.48 0.433 psi per foot, that's the normal pressure, to 0.875, that's the different over pressure. And the pressure increase across the seal was 4,000 psi. Anything lenticular sandstone within the sealing shale may take on the pressure ramp up sound in the shale, and catastrophic blowout can occur. So the next hydraulic fracture shales refer to a phenomenon where the rocks are prone to be breaking or fracture when the pressure caused by buoyancy, fluid injection surpass the minimum horizontal stress, known as fracture pressure or SH min. This pressure can be influenced by pore pressure, buoyancy of hydrocarbon column, and the overburden pressure or SV. It is important to note that columns cannot be exceed the fracture pressure to the maintain integrity of the hydraulic seal. Rocks are expected to fracture when the pressure caused by buoyancy or fluid injection surpass the minimum the horizontal stress, known as the fracture pressure SH min. This means that if the pressure exerted on the rock exceed their ability to withstand it, they will likely break or fracture. So, putting all together the role of pressure in the subsurface complexity with some definition identified following shale facies, shale variability, deep water depositional setting system. Let's say some description of the type of facies. Type 1 with well laminated, high clay content, high organic TUC deposit in deep water. This is going to be best cell capacity. It's around 8,395 psi, 10% mercury capillary pressure, mesoshale or capacity. The second type is some lamination, high clay content but lower than type 1. More silty than type 1, as well as more carbonate, high organic content. And it could be the next best seal capacity is around 7,445 psi MICP. The type 3, more silty and carbonate than type 2, but lower organic content, mottled texture, deposit in slope setting, less good shale capacity is around 4,950 psi MICP, while the type 4, more silty, carbonate than type 3, lower organic content, mottled silty texture, deposit in slope system, less good cell capacity, is around 3,175 MICP. The next type 5, of course, is still maintained in the same properties, but the cell capacity is lower, around 1,360. And the last type, number 7, a cell that has had enhanced mentation, reducing porosity and permeability, massive with few sedimentary structure. Normally, the cell capacity is around 7,665 psi MICP. Type 1, 2, and 6 laminate cemented cell form the best cell, while the slope stone form poor cell. Organic content was related to increased cell capacity, while silt and carbonate content was related to the poor cell capacity. And also introduce a bit detail, all explained earlier. Pressure within the fluid contents in the rock, they contain increase with depth due to increased thickness of overburdened rock according to the formula. Rho multiplied gamma multiplied H equal with pressure, where rho fluid density, gamma is gravitational constant, H is height of the column. So brief definition, as explained earlier, series of pressure definition. Pore pressure is pressure of the fluid content in the pore within the rock caused by weight of the fluid column only. Normally, pressure rock, this pressure lies the hydrostatic gradient range 0.433 psi per foot and up to 0.465 psi per foot, depending on the fluid density. The second pressure we call lithostatic gradient, pressure exerted by weight of the rock and fluid in the overburden. The gradient varies depending on rock type, normally about 1 psi or 23 kPa kilopascal per meters. The third pressure we call with fracture pressure, fracture, the pressure at which the rock would begin to break down and form the fracture. If the pore pressure exceeds the rock fracture, then fracture develop, allowing the fluid to leak. If the fluid are hydrocarbon, then they will leak upward, breaching the trap. So fracture gradient typically about 0.7 psi per foot or 15.8 kilopascal per meter, depending on the lithology. The next pressure is pore pressure, when the pressure within the pores is higher than the predicted by the hydrostatic gradient, and this can be due to the aquifer or reservoir being isolated during rapid boreal sedimentation. And the next is hydrocarbon pressure. Particularly gas is less than water. They have steep pressure gradient. Is typically 0.08 for gas and 0.35 for oil. Datum. On the land, all pressure are measured relatively to the ground level. Offshore, fluid pressure would be measured from sea level or lake level, but rock pressure measured from the seabed. This means the datums can be significantly different level when drilling in deep water, which much narrower gap between lithostatic and hydrostatic pressure level, leading to the weaker shale. Capillary entry pressure. It is a measure of inherent sealing capacity of the rock. This is the pressure needed to enable non-mixable fluids such as hydrocarbon to displace another fluid such as water within the pores of the rock by overcoming the surface tension. CEP depends on porosity, pore size, shape, as well as exact fluid properties or wettability. Smaller and more tortuous pore leads to the higher CEP, hence can hold back a greater hydrocarbon column. Capillary entry pressure are measured on the rock sample in a laboratory by injecting mercury, and the most common cause of seal failure is when the pressure exerted by the buoyant hydrocarbon exceeds the capillary entry pressure of the sealing rock, allowing hydrocarbon to percolate upward. So moving to the next slide, the occurrence and distribution of overpressure taken in the North Sea region, specifically Cretaceous and Jurassic reservoir, as well as the role of chimerate clay as a source of the overpressure. This schematic illustration of the stratigraphic section from central North Sea with typical pressure versus depth plot on the left. Tertiary clays are overpressure above the regional extensive subcropping. Paleocene reservoir is younger, and fluid escape allow equilibration to the hydrostatic pressure in the reservoir due to transference. In the deeper Jurassic shale, transference of pressure lead to higher than expected pressure at the crest of each confined fault block. So, back to the uncertainty in the predicting pore pressure, which is the pressure exerted by the fluid within the rock formation, can be addressed using various methods. This method include analyzing seismic velocity, studying data from nearby well, considering regional trend, and utilizing basin modeling. It is important to note that the actual pore pressure rarely aligns precisely with single predicted value, but instead varies within a range that is ideally defined by the predictive methodologies employed. This approach helps establish a range of uncertainty in the predicted pressure values rather than providing a single deterministic value. By considering these factors, engineers and scientists can estimate the pressure level with certain level of confidence, considering the inherent variability of the prediction. The actual pressure in a geological formation rarely matches in a single predetermined value, but instead varies within the range. This variation is not due to chance, but influenced by predictive methodologies such as seismic velocities, offset well, regional trend, and basin modeling. These methodologies aims to define A range of uncertainty within actual pressure is expected to fall, providing a valuable insight for drilling and resource exploration. The mentioned models successfully predict significant change in pressure, the Miocene unconformity, the Miocene Oligocene boundary, the specific well data at 471 and 84 330 F1 highlight the importance of accurately recognizing pressure increase at the base of the Miocene interval. This recognition lead to cost and time saving in drilling operation, specifically in relation to depth at which 16-inch pipe installed. The concept of minimum stress, also known the fracture uncertainty, refer to the ratio of the minimum effective stress to the maximum effective stress. It is represented by the variable of K, which can be calculated using formula K equal with S minimum minus pore pressure divided S max minus pore pressure, where S minimum represent the fracture pressure or minimum stress. Pore pressure varies within the range, and the S max is maximum stress that depends on factors like water depth, sediment bulk density. The values of K is influenced by the lithology, degree of consolidation, age, and the tectonic regime, and it's commonly determined through casing shoe leak-off test. The calculation of fracture pressure or minimum effective stress based on the ratio of the minimum effective stress to the maximum effective stress K. The formula is given as minimum is equal with pore pressure plus K multiply as max minus pore pressure. The pore pressure represents a variable within range, and S max is the maximum effective stress. This equation allow for the determination of fracture pressure by considering the relationship between these stress parameters. Pore pressure varies within a range, mean that pore pressure, which represent fracture pressure or minimum effective stress, can have different values within a specific range. The values of S max, which represent maximum effective stress, depend on the water depth and sediment bulk density in extensional regime, either vertical or horizontal in compressional regime. The value of K, which is ratio used to calculate fracture pressure, varies based on factor lithology, degree of consolidation, age, and tectonic regime, then can be determined by effective through casing shoe leak-off test. Fracture gradient, which indicate pressure at which rock fracture, can be estimated using equation, but typically measured through a test called leak-off test in well. During this test, pump pressure are increased until fluid leakage into the formation is observed. Plotting this point on the pressure versus depth graph provide better approximation of the fracture gradient, and it is crucial to avoid exceeding the fracture gradient while drilling to prevent the blowout. And if the pore pressure approach the fracture gradient, it hinders the accumulation of hydrocarbon columns due to the shale failure and loss of the trap. The use of leak-off test to find the fracture gradient is one of the methods employed to determine the pressure at which fracture or crack occur in subsurface formation. By measuring the pressure required to initiate fracture, engineers can assess the strength of the rock and its ability to hold the fluid. This information is crucial for especially for the drilling activity and hydraulic fracturing operation to prevent unwanted fluid migration, ensure safe, efficient extraction of the resource. And the use of leak of test directly measure the fracture gradient in the contact, the pressure required to create fracture in the subsurface, and leak of test very valuable information about the rock strength, pressure at which fracture occurs, aiding the understanding of subsurface condition and hydrodynamic. So another term, leak of depth versus depth below mud line. A study or analysis conducted in deep water region of the Gulf of Mexico. The purpose of the study investigate the relationship between leak of test, which measure the pressure at which fluid leaks into surrounding rock formation during the drilling operation, and the depth below of the mud line. This analysis help us understand how factors like water depth, pore pressure, effective stress ratio affect the fracture gradient, which is important for safe drilling operation. And the variation in fracture gradient, which is the pressure required to initiate or propagate fracture in subsurface rock. This variation is influenced by three factors, normally water depth, effect of overburden, vertical stress, and the second one is pore pressure, and the third one effective stress ratio. All of these factors is significant role determine strength and stability of the rock formation, particularly deep water environments like Gulf of Mexico. A range of fracture shell capacities can be achieved due to variation vectors that are both independent and dependent on each other. This factor can influence the ability of fracture to seal, which is important understanding the behavior of fluid flow in subsurface, and emphasize the complexity, variability of these factors, highlighting the need for careful consideration when predicting fracture shell capacity. The maximum column height in a well can be influenced a number of factors, including the fluid gradient, shale pressure prediction at the well, fracture pressure prediction, and the centroid. The varying this factor height of the column of fluid in the well can change. It is important to note that centroid, which represent point where the pressure in the cell equals the aquifer pressure, commonly assumed to be at the well location, but may be incorrect if the well testing up deep on the structure. As we can see the following slides, a certain part pointing the specific term of the pressure. So let's look at on each. Fracture pressure uncertainty, the lack of precise knowledge, variability in predicting the pressure required induced fracture in the rock. This uncertainty arises due to multiple independent, variable dependent factors such as weight gradient, shell pressure prediction, fracture pressure prediction, and location of the centroid. The next term we call predicted fracture pressure, an estimation of the pressure at which fracture or crack may occur in geological formation such as shale. And this prediction influenced by uncertainty in shale pressure, aquifer pressure, fracture shale capacity. It is important to note the most method assume the centroid point of equal pressure between shale and aquifer located at the well, but this assumption may be incorrect again when the well position is up deep of the structure. So the next pressure they call shale pressure uncertainty. Again, the lack of precise knowledge or uncertainty associated with the pressure in the shale formation. This uncertainty due to various factors, almost similar with the previous one. The next pressure we call it aquifer pressure. the pressure exerted by groundwater within underground reservoir or aquifer. It is important parameter to consider in various applications, as it can impact the stability of formation, the potential for fluid migration. Aquifer pressure is mentioned as one of the factors that can contribute to the uncertainty in predicting fracture pressure. The next term is predicted shale pressure. Estimated pressure in the shale formation indicate that predicted pressure may not be entirely accurate or reliable. Suggested that there is uncertainty associated with the predicted pressure in shale formation, can be influenced by number of factors. Again, fluid gradient, fracture pressure prediction, shale pressure prediction as well. And in the contact predicting fracture pressure, most methods estimate the pressure in shale aligned with pressure in aquifer at single point, known as centroid. However, it is commonly assumed that the centroid located at the well position, again, may be incorrect. So this highlights the importance of considering correct location of the centroid when assessing the fracture pressure prediction. Fracture sealing in the context of oil and gas, few recommendation utilizing a reliable method to predict pore pressure and fracture pressure while considering the uncertainty associated with this prediction. Additionally, guidelines should be established to determine appropriate hydrocarbon fluid gradient in the basin wide where there is limited no fluid data. And lastly, sound methodology should be developed to incorporate water and hydrocarbon column pressure into predicted shale pressure profile. Suggested procedure to provide is an appendix, the next few slides. So to ensure the integrity of well drilling operation, it is also recommended to use suitable method for predicting pore pressure and fracture pressure. Additionally, it is important to assess uncertainty associated with this prediction. Helps in making informed decision, mitigating risk during exploration and drilling activity. Suggested that establish guideline determining suitable hydrocarbon fluid gradient, particularly in basin where there is no limited or even no available fluid data. This guideline would help predicting the appropriate pressure profile for shale formation, incorporating information about water, aquifer, and hydrocarbon column pressure. I think this is a number of published paper that use as a reference supplemental materials listed under appendix. Extrapolate curve were obtained from a study conducted by Roch et al. In 1951. The study focus on interfacial tension between gas and water, specifically methane and water at different temperature and pressure. The use of nomograph, a graphical tool to estimate the interfacial tension of methane and water under varying temperature and pressure condition. Gas water interfacial tension, force or energy required to separate gas phase from liquid water phase at their interface. It is measure of the attraction or repulsion between the gas water molecules at the interface. This property plays a crucial role in various natural or industrial process such as bubble formation, droplet stability, or even oil water separation. The oil-water interfacial tensions force between oil-water at the interface. Uh, this nomograph introduced a graphical tool used to estimate this tension at reservoir temperature. The nomograph shows for every 1 degree Fahrenheit increase in temperature, the interfacial tension decreased by 0.19 per centimeters. It is important to note that there is a wide range of published value for oil, which can vary depending on the type of hydrocarbon present. The term oil-water interfacial tension force energy required to separate oil and water at the interface, measure of the attraction repulsion between oil and water molecules, suggests that there is a wide range reported values for this interfacial tension. May vary depending on the type of hydrocarbon. Additionally, the inference drawn is that oil may not effectively sail above the temperature above 250 degrees Fahrenheit due to the observed variability in the interfacial tension values. In other words, the wide range of values found in published literature for the interfacial tension between oil and water. The variability is attributed in different type of hydrocarbon present in the oil. In simpler terms, the interfacial tension, which affect the ability of oil to form a shale, can vary significantly depending on the specific composition of the oil. The inference suggests that oil doesn't have the ability to effectively shale or prevent leakage at temperature exceeding 250 degrees Fahrenheit. And this conclusion is drawn from the wide range of published value oil-water interfacial tension, indicating lack of consistent sealing capacity for oil under higher temperature condition. The next slide, technique for applying pressure gradient, the maximum sealing capacity. This technique involves using varying level of pressure to assess the ability of shale prevent leakage or maintain tight shale. By applying different pressure gradient, the maximum sealing capacity of the shale can be determined. The next slide, we may call it a advisor web-based column estimation tool that estimate the height distribution of column for fault and top shale based on user input and limited database. It requires general geologic data, clay content of the critical fault juxtaposition as an input. Output provide the estimated column height distribution for fault and top shale, aiding in assessment of shale risk in prospect zone. A general info with the question sheet, where these questions are used to categorize the prospect input into the database, used by the column head advisor to calculate a fault shale column. And the PVT with data is very important for the column height calculation. It's explained that estimated column height determined based on the user input and utilize a limited local and worldwide database. The tool takes general geologic data, clay content of the critical fault juxtaposition, and provide the output column height distribution for the fault and top shale. It is web-based tool called Shale Risk Advisor. Just an idea to share that for common procedure for prospect generation evaluation in oil and gas industry. Um, in the step number one, we need to determine the height or elevation various point in the reservoir system. This include the top or bottom reservoir, the well penetration point, the structural spill point, if relevant, and the predicted pressure of the shale formation. These elevation measurements are crucial for understanding geological characteristic and pressure distribution within the reservoir. The term predicted shale pressure, this is step number 2A, shows the estimation of the pressure exerted by shale rock at specific well location. In the given context, this pressure is extrapolated from the gradient referent to surface datum such as sea level, then projected further down along the interface between the shale and sand layers. This step help in understanding the pressure distribution within the reservoir system, and also shale gradient referring to origin, change in pressure per unit depth within shale layer measured from specific reference point. This gradient used to predict the pressure distribution along the shale sand interface by extrapolating it from the well location to other areas of interest. It helps in understanding the pressure variation within reservoir system and is important factor drilling and reservoir engineering purposes. The base of reservoir system refer to the depth at which reservoir system ends or transition into another geological formation. Predicted shale pressure, an estimation of pressure within shale rock layer. In the step 2B, it is advised not to extend the predicted shale pressure profile beyond its known range, as doing so would result in extrapolating the pressure downward along the wellbore instead of in the down deep direction. In the context of reservoir system, determining the centroid depth is an important step. The centroid depth, as explained earlier, the depth at which the pressure of shale formation, pressure and the sand formation are equal. While the midpoint of the reservoir system is often used as a reference, the actual centroid depth depends on the geometry of sediment overburden that lies above the reservoir. Shale formation pressure refers to the pressure exerted by shale rock layer. It is determined by measuring the pressure along the vertical section of the shale formation, also along the boundary between shale and shale layers. The pressure of the shale formation influenced by sediment overburden, which is layer of sedimentary rock, lies between above the reservoir system. The centroid depth within reservoir system where the pressure exerted by shale formation, sand formation equal. This depth typically considered to be a midpoint of the reservoir system, but it can be vary depending on shape and characteristic of the sediment overburden above the reservoir. So in the contact reservoir system, a shale formation pressure exerted by the shale rock layer determined by measuring pressure along vertical section through the shale formation along boundary between shale and shale layer. The pressure exerted by shale formation along boundary and shale sand formation in the context determining the centroid depth of the reservoir, shale pressure along the boundary is significant because it plays a role in finding the depth where the pressure from shale and sand formation are equal. This depth is crucial, again, understanding the behavior of the reservoir system, it's overlying the sediment overburden. In So the next given term, the top of reservoir system, base reservoir system indicate the lowest point of the reservoir, predicted shale pressure, estimated pressure accepted by the shale rock formation within the reservoir. So in the step 4E, water gradient aquifer pressure is extrapolated from the centroid, the top of reservoir, and depth refer to the vertical distance below the surface. Pressure represent the force per unit area, and water gradient indicate the change of water pressure with the depth. In step 4B, instruction to verify that the water pressure in the up deep region doesn't surpass the fracture pressure. If it does, there is no seismic evidence of breakdown. There are three possible explanations. Either the pressure in the sand is not balanced with the pressure in the shale, the centroid needs to be shifted upward, or shale pressure need to be reassessed. The diagram show the relationship between depth pressure, sand pressure, shale pressure, and fracture pressure. In the step number 5, the hydrocarbon gradient is added to the water pressure line to calculate the maximum height of the hydrocarbon column in the reservoir. This calculation considers the depth, pressure, fracture pressure, hydrocarbon pressure. It helps determine the limitation imposed by structural or fracture pressure on the height of the hydrocarbon column in the reservoir. So a number of scenario has been exercised, while scenario number 1, the maximum height of the hydrocarbon column in the reservoir is determined by the structural features of the reservoir rather than the pressure. This is because the pressure at the top of reservoir doesn't exceed the fracture pressure, which is pressure at which rock formation would break allow fluid to escape. Scenario number 2, based of the reservoir system as the lowest depth at which the reservoir rock formation extend, indicate the vertical distance from surface at specific point in the subsurface pressure. Force exerted fluids within the reservoir, while the fracture pressure required introduce fracture to rock formation. In scenario number 2, concept fracture control on the maximum column suggests that fracture in the formation should occur, allow additional hydrocarbon fluid escape before the column of hydrocarbon accumulates and reach the spill point, preventing the potential spill or leak. The hydrocarbon water level, which is defined fracture control to the level at which hydrocarbon water are separated within the reservoir system. And this level determined by the control exerted by fracture information. The fracture acts as pathway to release additional hydrocarbon, prevent the accumulation, and hydrocarbon column to be the point of spilling over. The third scenario, there is no structural spill point, meaning there is no natural pathway for hydrocarbon to escape. Therefore, maximum height of the hydrocarbon column is determined by the fracture pressure, which is pressure required to create fracture in the reservoir rock, allow hydrocarbon to flow. This indicates that fracture pressure set the upper limit of extend the hydrocarbon accumulation in this scenario. Possible leak point refer potential location or point of reservoir system where there could be leakage or escape of fluids such as hydrocarbon or water. This term indicate the existence of potential weak spot or pathway that may allow fluid escape from the reservoir. Um, I think that's all at the moment, all of the presentation, the knowledge sharings. Thank you for all listening. Hope everybody enjoy it. And wassalamualaikum warahmatullahi wabarakatuh.